B.2, general solution of binary bits problem. From the last video, we solved this problem, but it is for a very special case. N is the power of 2. We're not satisfied with that. We need to solve the problem for the general n case. Any positive integer n, we can get the answer. All right, so this video, we will do it. The strategy. Yeah, so here we use a strategy. We use it several times before. So that is guess and verify approach. We guess the correct result. We try our best to guess a result. Sometimes it may not be correct, your guess. Then you can make adjustment later. But guess first. Then we verify it. So from the last video, our guess is this. Okay? And this guess comes from power of 2 case. So we have some very good reason to make this guess. In this video, let us verify it. Okay. To verify it, we need to use a very powerful mathematical tool, mathematical induction. So that is a big part in your discrete math, mathematical induction. Now we need to use it here. To use the mathematical induction, we have 3 steps. Okay, so we follow that 1, 2, 3 steps to do it. The first step, verify the base case. That's easy. Usually that is the easiest step. Base case, we're plugging 1 into the formula both sides. We want to check if it is correct or not. 1 plus log base 2 of 1. So this is 0, right? Log base some, positive number, not 1. Here. When I talk about here, I just want to remind you, when we use the log base a, 1 equals 0, right? So we have that. But this a, we have the condition. A greater than 0, that's the first condition. Second, a cannot be 1. Otherwise, this log expression is not defined. Okay? Here, I just, remind you that the basic property. So here we get this number 1, so we verify the base case. Correct? Step 2, we make induction assumption. This step, we just make assumption. We do not need to prove anything, right? But this is an important step. So let's see what kind of assumption we should make for this step. All right. We assume the formula, this is correct for k in the range between 1 and n. That is our assumption. Certain n. So this n is certain n. Okay? We assume it is correct when k between 1 and n. That's our induction assumption. At this point, I want to remind you a little bit. When you learn the mathematical induction, there are 2 versions. Version 1, version 2. Okay? The first version, version 1, a little weaker than version 2. Here, we are using the version 2. Okay? Type 2, whatever people call type 2. Type 1, our induction assumption, we make k equals n. For k equals n. Okay? But induction version 2, we assume more, a little more than induction, between 1 and n. So we assume a little more but actually these two versions are equivalent. Although you see assumption, we assume a little more, but mathematically they are equivalent, both true. Yeah. But under the current situation, version 2 easier to use than version 1. If you use version 1, in some steps, you cannot apply this assumption. But version 2, you can. Okay? We will see that. Yeah. All right. Now we are ready to work on the hardest step, step 3, when n equals n plus 1. Okay? So the number 1 higher than the range, than the largest number in the range of your assumption. 1 higher than that. Okay? So that is the basic idea of mathematical induction. If you can prove when k equals n plus 1, this formula is still true, then you prove the whole thing. The formula is true for all n positive integer case. Yeah. All right, let's start a proof. Yeah. The proof is a little hard. Yeah. Here we need to use a lot of math related to the logarithm and the floor function. These two functions, mainly we use formulas. Yeah. In the proof, we divide it into 2 halves. Okay? The first half, when n is an odd number. Yeah. Here, because there is a log base 2, yeah. That means with better, we consider even odd number. Because even odd number, there is a property. When you divide it by 2, the remainder is 1 or 0. These two cases. Yeah. So divided by 2. When you do division by 2, it is good for log base 2. Yeah. So that kind of intuition is important in math proof. Yeah. Here we use that. Yeah. So let's start to see the details of our proof. Yeah. When n is an odd number, we can assume it takes this form, 2s minus 1, with s greater or equal to 1. Yeah. When you do this assumption, we can do formula manipulations, and we can use many properties, formulas of log and floor functions. Yeah. Left-hand side first. Yeah. We want to verify this formula. So this formula, you have left-hand side, right-hand side. Okay, left-hand side, right-hand side. Here, we start with the left-hand side. Okay, yeah. Left-hand side, let's do that simplification. Yeah. All right. So now we replace n by 2s minus 1. So we get a of 2s. Yeah. Then we apply the recurrence relation. Remember recurrence relation, a of floor function, 2s divided by 2, right? Yeah, so that is s. Yeah, that is s. Yeah, so we get this form. Yeah. Then, next step, we can use the induction assumption step. Okay? Yeah, we plug in s here. We should have s there by induction assumption. Yeah, so we get this. But why we can use induction assumption? Here you need to prove s falls into the range, then you can use. If s is outside the range, then you cannot use. Yeah. Here, let's try to look at the range that cover s. Yeah. S, how to get s? In terms of n. From here, you plus 1 both sides divided by 2. So s equals n plus 1 over 2. And this expression is less than n. So you can see easily, right? You multiply 2, this side, n minus plus 1 less than equal to 2n. Okay? 1 less than equal to n. This is correct, right? So this S expression is less than or equal to n, so definitely greater or equal to 1, right? No problem. Yeah. So S falls into this range, so we can apply induction assumption. Yeah. Otherwise, we cannot. Right? Now we have no problem. So this is our left-hand side expression. So let's put there. Okay, we go to right-hand side and see if we get the same thing as the left-hand side. Yeah. All right. So when we go to the right-hand side, yeah. So let's do here. Yeah. Right-hand side, this expression, yeah. Replace m by 2s minus 1, right? So we get the 2s. Yeah. Now let's do some formula chain. So log base 2 times s. Do you know this property? Log b of x times y equals log any base x plus log y. Do you know that formula? Here we use that. Okay? So log base 2 of 2 plus log base 2 of s. But log base 2 of 2, that is 1. Okay? So 1 plus log base 2 of s. 1 plus log base 2 of s. See? Yeah. That's the formula transformation. Yeah. But here, to simplify this floor function part, we need another formula from our textbook. So here, let me put here the formula from our textbook, Appendix A, this page. So you can find it. Yeah. It tells us when you calculate the floor function of x plus an integer, here n means some integer, okay? Could be positive, negative, 0, doesn't matter, but it must be an integer. If you see integer inside that floor function bracket, you can pull it out directly, okay? Yeah, so pull it out of the floor function brackets, yeah, okay? So here, we can pull that 1 out, okay? So we get a 2 plus log base 2 of s. So you can see after that, this right-hand side. So this is the right-hand side. Right-hand side equals this. Okay. You can, when you compare left-hand side expression, right-hand side expression, they are exactly the same. Okay. So that means for n is odd number, we verify. Our guess is correct. But that's just 1/2. Okay? That is just an odd number. Next, we need to do that even number case. Yeah. All right, so this side, let's do the even case. When n is even, we represent n as 2 times s. Okay? So we still use the same way as we used before, but this time we need to use our formulas for the new expression of n. Yeah. All right, so left-hand side, we still look at left-hand side equals this. Yeah. 2s plus 1. Yeah. Remember 2s plus 1 by the recurrence relation, 2s plus 1 over 2 floor function. Floor function, so that 1 is gone, right? Yeah, fractional part. So you get a of s plus 1. Okay. This a of s, this part, induction assumption, another time. Okay, so we just use induction assumption another time. Okay. Yeah, so we get this. log base 2 of s flow function plus 1, so 1 plus 1, 2. Now, here, why we can use induction assumption, you need to check the range for s. What is the range? S equals n over 2. Definitely it falls into the range between 1 and n, right? So we can use induction assumption. Okay, it is legal. Yeah. So now we get expression of the left-hand side, this. Yeah. So let's put there temporarily. So later we will use it to compare with the expression of the right-hand side. Okay. Now let's work on the right-hand side. Equals this. Okay. Plug in, yeah, 2s plus 1. Yeah. So n to s, right? 2s plus 1. Okay. Now this part, this is the hard part. Okay. This is the hard part. How to process, how to do the transformation on this formula. This is the hard part. Yeah. We need to use a special formula. Now, if you do not know this formula, it is very hard. Yeah. So let me give you the formula. This is the formula. Ceiling function, look at here. Ceiling function, log base 2, n plus 1. Okay. Here, flow function. Okay. Flow function. And 1 get out. Okay. Take that 1 out of it. This formula, this two sides equal. Okay. Yeah. It is not easy to prove it, but it can be proved. Yeah. It can be proved. Yeah. All right. Yeah. This one, I give you the reference. Appendix A, this page. Yeah. So you can see it. Yeah. Later you can use it. Now we need to use it. We need to use this formula. All right. Let's start. Yeah. Now we need to simplify this expression. Yeah. How to do it? So this expression, how do we get this? Yeah. All right. Flow function, right? Look at the flow function here. That's the flow function here. Okay? Yeah, we use that. Flow function log base 2 of n equals ceiling function log base 2 of n plus 1 minus 1, right? Can we replace n by 2s plus 1? If you replace it by 2s plus 1, you get this expression. Here, 2s plus 1, n plus 1, so 2n plus 2. Yeah, this. So you get this expression. All right. After that expression, then this one, 2 times s plus 1, right? Then this one we can split. Log base 2 plus log base 2 s plus 1. Okay? Yeah. Minus 1. Okay? Yeah. This is 1, right? So this expression is 1. Yeah. This one we can pull it out of the ceiling function. Yeah. Same as the flow function. Yeah. For ceiling function, we have the same thing. Okay. X plus n. Ceiling function, we can take the integer n out. Okay. We can take it out. Yeah. Same reason. Yeah. So here we can take that 1 out. 1 out, net minus 1 cancel out. Okay. Cancel out. Then 1 is gone. Remaining part, ceiling function log base 2 s plus 1. Yeah. Hope you can handle the math like this. Yeah. All right. After this, okay, yeah. So you get this point. You put it back. Okay. Yeah. Yeah. All right. Yeah. Before we put it back, we move another step. How do we get this? This formula another time. Okay. Ceiling function, this time we use s replace n. Okay. So you get the bottom formula. All right. After that, then you put it back. So you get floor function of log base 2 of s plus 2. Exactly the same as the left-hand side. So after your comparison, you show this formula also correct for the even case, for n is an even number. So you prove all the cases, you verify, all the cases, so the result is correct. So finally, you prove our guess is correct by mathematical induction. All right, so that's video part B.2. Yeah.